Now with water, pure water does not conduct electricity very well at all. And if I was to set up a beaker, with pure water in it and put a set of wires coming down and connect it up to some electricity and a light bulb, all right, and we put water in here, pure water, like distilled water. It has nothing in there but water molecules. It's a pure substance, pure compound, pure water. And I hook this up to some electricity. That light bulb will not light. The electricity will not be able to go from one wire to the other to complete the circuit, just like closing a switch when you turn a light on and off in a room. Well, it's the same thing right here. We're trying to use whatever's in here to close that switch. Now, to get electricity to flow between these wires, you need ions. Ions are what the electrons are going to hitch a ride on. So the electrons can't move from here to there for electricity, but they can hitch a ride on ions. Ions allow the electricity to flow, just like that. So it flows, and if the electricity is flowing, if the electricity is catching a ride on these different ions, the light will light. This will complete the circuit between the two wires, and you will have the light will light up. Now, these ions here, you're required to have ions in water. It's in water. That's how we're getting this to have the electricity flow. Now, when we have ions in water, we call this an electrolyte. That's a compound that produces ions in water. And so an electrolyte is a compound that produces ions in water. Now notice I underlined ions and the water. That's because you have to have both to have an electrolyte. It has, when it dissociates, and more on that in just a bit, when it dissociates, whatever that compound is, it's associating in water. And when it dissociates in water and produces ions, you now have something that can carry, the electrons can carry the current in between the two wires. So we'll call that an electrolyte. So anytime you put an electrolyte in this apparatus right here, it's going to allow the circuit to flow and the light will come on. Okay, so we have strong electrolytes. So we have strong and it dissociates completely. That's what it means to go to all ions. And so when it dissociates completely, it's all ions, no molecules. All ions, no molecules. Now, if it's strong, we have all ions, no molecules, no starting molecules. But if it's a weak electrolyte, the situation is different. A weak means it does not dissociate completely. It does not. A weak does not dissociate completely. And the way we're going to draw a weak electrolyte might be something like this, where say we have hydrofluoric aqueous, say it's already in water, and that goes to H plus aqueous plus F minus aqueous. Now, let me draw up here one of the previous ones that we just did. Let's say we had that sodium sulfate up here, and it dissociated into the 2 sodium pluses plus the SO4 2 minus. Can you notice the difference between these two equations? Well, the only difference that I see, besides that they're different things, is this one right up here, the sodium sulfate going into the sodium ion plus the sulfate ion, is that there's one arrow. And down here we have 2 arrows. Now this is very important. When we have an equation that has an arrow, has a single arrow, that means we're going completely to products. Means that nothing, after we've done this, after we've dissociated, is there's none of this left, no starting molecules, and we're all over here. That's what a single arrow means. Now, if I have 2 arrows, what it means is that as you form the product over here, as they dissociate to form the hydrogen and the fluoride ion, they will also recombine and go back to the other way to the original molecule. Now, in this particular equilibrium, because that's what that means when you have a double arrow, this is going to be mostly molecule that's dissolved with few ions. And in fact, for hydrofluoric acid that's dissolved, it's about 10,000 to 1. There's about 10,000 of the hydrofluoric molecule dissolved, and only about 1 out of 10,000 ends up dissociating into the H plus and the fluoride ion. So mostly molecule, few ions. And so when we have a weak, we are mostly molecule, few ions. Now, mostly and few. Now, the fact that we're producing some ions still makes it an electrolyte. Remember, an electrolyte, I didn't say anything about how many ions are producing. All that you need for something to be an electrolyte is that when it dissolves in water, it does produce ions. It might not be very many ions in the case of a weak electrolyte, but they're still there, and that's what you need to be able to conduct electricity, where we get the word electrolyte from anyway. And so this will be mostly not ion. So if we're trying to conduct electricity, then we will get some electricity conducted, but it won't be as much. And our light bulb, if you recall our light bulb experiment, will be dim, because you need ions to be able to conduct electricity, and there's not very many of them. You'll conduct some electricity, and light bulb will be dim. Whereas a strong electrolyte is all ions. You have plenty of ions, and you'll be able to conduct electricity very well with our light bulb experiment. And so the light ends up being very bright for strong electrolytes, very dim for weak, very bright for strong. Now, there is one more kind, and it's a non-electrolyte. To dissolve something, you don't have to produce ions for something to dissolve. And so it does not produce ions. In water. Now, things do dissolve. Things do dissolve without producing ions. An example would be glucose, which is C6H12O6, otherwise known as blood sugar. And glucose is a sugar, and if you recall, what does sugar look like when it's in the sugar bowl? It's solid, it's crystals. And when you stir it into water, what happens to the sugar? It dissolves. So it goes from solid to being aqueous in water. But glucose is a molecule. It's not an ionic compound. And so when it dissolves, it goes from solid to aqueous, but you don't see any ions over here. There's no ions that are coming off of the glucose, not like up here where it fell apart and dissociated into ions. Down here, when glucose, you stir it into your water, and you end up with aqueous glucose that's in solution. Remember, to be able to conduct electricity, you have to have ions. And if you don't make ions, it doesn't conduct electricity. So a solution of glucose will not conduct electricity in the light bulb experiment, so the light bulb will actually not turn on at all. Whereas with strong, it'll make a light bulb bright, and with weak, it would make the light bulb dim. Non-electrolytes, no producing ions, doesn't produce any ions, therefore it cannot conduct electricity, a solution of glucose. So there you go, you have your three kinds of electrolytes. You've got strong, weak, and non. And I want to mention that in terms of chemistry, when we see strong, strong does not mean dangerous. Strong just means dissociates completely. And weak does not mean that it's safe. Weak just means it dissociates not completely. And an example would be, the difference in safety is sodium sulfate is very safe. You can soak your feet in sodium sulfate, no problem. Hydrofluoric acid is a weak acid. It's a weak electrolyte, but you can't store it in glass because it will actually eat the glass, and it will actually, if you got some on your skin, it will damage your skin very badly. Even though it's weak, it's still dangerous, whereas this is strong and it's not dangerous at all. So that's all that strong means. It dissociates completely. That's all that weak means, is that it doesn't dissociate completely, but does dissociate some, and non-electrolyte means it doesn't dissociate at all once it's dissolved in water.